Welcome back, everybody. This is AP Chemistry, Unit 10 with gases, and we're in Section 3 taking a look at some different applications with the gases in terms of adding them up, taking a look at different molar masses, and so on. So different applications is the theme for Section 3. So the first application we're taking a look at is actually a review of what we saw a little bit of in Section 2, where we were collecting a gas over water. And we saw when we collected a gas over water, we were adding up the water vapor pressure as well as the dry gas to get the total pressure. But we can do this to do other types of problems as well, because Dalton's law of partial pressure states that basically when you have a system of something, the pressure of that system is just the sum of the individual gases that's in there. So here's what we mean by that. If we take a look at a mixture of just helium and hydrogen gas, okay? Now, when I say mixture, this is not a chemical reaction. Be careful. We're just taking a look at the helium and hydrogen mixing within this 1 liter container at 27 degrees. So if I track this, there's actually a couple ways I can solve this problem. If I track this a little bit, I'm given my hydrogen, and I have 1.00 grams of hydrogen. Well, if I say there's 2.02 grams of hydrogen for every mole, if I have 1 gram of hydrogen, that means I have 0.496 moles of hydrogen gas, okay? And so if I see that, I also have the helium now is going to be 1.00 grams of helium, and that has a mass of 4.00 grams per mole. And so the amount of helium that's in that system is going to be 2.50 moles of helium gas. Okay, so there's a couple ways that I can do this. Like I said, I'm going to do it kind of the slower way, and we're going to do the ideal gas law for both individually. Okay, so the pressure of my hydrogen, I'll just keep track of that. It is a 1 liter container, and we found that we had 0.496 moles of the hydrogen gas, and I have 0.08206 is my constant, and it's at 27 degrees Celsius, which is in fact 300 Kelvin. Okay, so if I'm looking at this, I have 12.2 atmospheres of hydrogen. Okay, now let's do the same thing for pressure for my helium. Okay, it is a 1 liter container, and I have 0.250 moles. 0.08206 is my constant, and the temperature is once again 300. And so I have 6.2 atmospheres of helium. Okay, so Dalton's law of partial pressures says that I can simply add those up, and those two together will end up being 18.4 atmospheres total. Okay, now if I look at the problem and the prompt of what it's asking, I want to know the pressure of each gas as well as the total pressure, and so this would be the best way to solve for that problem. But if they were just asking for just the total pressure of the system, we could combine these together. See, if I use Dalton's law, and I could say the pressure of my hydrogen plus the pressure of my helium, because they just add up, it is a 1 liter container. Now, the number of moles does also add up, doesn't it? So I have my 0.496 plus my 0.250. That accounts for my hydrogen as well as my helium. 0.08206, and the temperature is going to be 300. And so I would end up with the exact same answer of 18.4 liters total. Or I'm sorry, this is going to be atmospheres, it's pressure. Okay, now that's only going to work if they want the total pressure, but since they're asking for pressure of each gas, you probably have to solve them in turn. Okay, so let's take a look at another problem with that, and we see a piece of solid carbon dioxide with a mass of 7.8 grams is put into a container that is otherwise empty at 27 degrees Celsius. We want to know the pressure of the container after all the carbon dioxide vaporizes. Now what's going on, a solid carbon dioxide is known as dry ice. And so that will sublimate. That will go right from a solid to a gaseous state. So if I have 7.8 grams of carbon dioxide, that's going to be a mass of 44 grams per mole. And so this will give me 0.18 moles of carbon dioxide. Okay, so I just simply go in and I say the pressure is going to be 4 liters times my 0.18 moles times 0.08206, and it is at, what temperature are we at? 27 degrees Celsius. So once again, that's 300 Kelvin. Okay, so the pressure of the system, if it was just an empty container, nothing else in it, I would have 1.1 atmospheres. Okay, so I plug that in and there's nothing in there. But the second part of this problem says if we're going to put it in but already had air at 740 torr. So what's going to happen is I have 1.1 atmospheres, but there's also the 740. Okay, so I have 1.1 atmospheres in there and I'm going to add in 740 torr. You see the problem, guys. You have two units that don't agree. So simply convert your torr over into your atmospheres. Really, you could convert your atmospheres over to torr if you want. You just have to get them to agree. But I simply don't have to rework everything. It just says, just add up your pressures. Okay, and then you'll end up in the same units. So pretty straightforward with those. I don't see any real problems with them as long as you just kind of keep visualizing what's going on with Dalton's law. Now, another thing, this is probably the biggest example of what chemists will do with gases is figure out the identity of a gas by using the density. Okay, so molar mass of something is going to be a function of its density, because remember, that's going to be in number of moles and things like that. Density times the R value times the T value times the P, and that's going to be in atmospheres again. But remember that density is mass over volume. D equals M over V. So I can derive this a little bit into mass over volume times my R times my T over P. Okay, so it's just simply going through and using those things because a mole is a relationship of mass and you have your volume in there. Okay, so let's take a look at how this works. And I see that I have my molar mass is what we're going to be solving for. Okay, and so I saw that I had the density is going to be mass over volume. So I have 1.96 grams per liter. Okay, so that's my density part. Now let's plug in the other parts. There's my 0.08206. My temperature is 27, so we'll use 300 here. And then I have just my pressure to account for. And it is in atmospheres, so 1.50 atmospheres. So you see, all I end up with is 32.2 grams per liter. Okay, so I look on the periodic table, what's going to be 32 grams? A lot of things are, but we would see something like oxygen would be like grams per mole and so on. It's 32 grams per mole because it's diatomic. And so I would say maybe it's oxygen, maybe it's something else. Okay, so straightforward with that. Just remember to derive that density part, and we're good to go. Guys, chemists do this all the time. They do atmospheric sampling. They do all these. They vaporize something. They see the density. This is what a mass spectrometer is really good for. Okay, so it's a good, useful problem. Now, we can also do other things and take a look at the ratio of something given to the total number of moles. Okay, and so if we do that, we see the number of moles of one thing equals the pressure of one thing over the number of moles total and total pressure. Okay, so this is kind of a different type of problem. Not my favorite problem to do, but let's go ahead and take a look at it anyway. We're going to be taking a look and seeing what the total pressure and partial pressure of each gas is along the way. All right, so to do that, I have to keep into account that I've got two different gases. I've got helium gas and I've got nitrogen gas. Okay, so let's analyze my helium first. Okay, so I have 1.2 atmospheres. It's 2 liters container, and I'm going to be figuring out how many moles that is, and that's 0.08206 times my temperature, which in this case was 319. And so I end up with 0.091 moles of helium. Okay, now I'm going to do the exact same thing for my my nitrogen. Okay, and so I have in this case 1 atmosphere, and it's going to be in a 4.5 liter container, and we have number of moles 0.08206, and my temperature here is going to be 273. And so I end up with 0.2 moles of nitrogen. Okay, so we're going to add in a certain amount, 2 liters, into this. Now, the vessel contains 4.5 liters of the gas. The vessel doesn't change, guys. Okay, so it's all going to be put into this. That means that I'm going to be adding those things in there. And so the pressure of the system is going to be a function of that 4.5 liters. This is why I wasn't a big fan of the problem, but you just got to conceptualize how we've got there. Now, we're going to be adding in the total number of moles. I have 0.291 total moles in there. Okay, so that's what I've got, 2191, and I'm going to end up with 0.08206, and the temperature ends up being 273. Okay, we're going to add it in there, and we would assume in this that it's going to be going to STP. They don't really give me the ending temperature in there, so I'll just pick that. I'll end up with a total pressure then of 1.45 atmospheres. Okay, so there's a couple issues with the prompt itself, but if we're just going to be adding it to STP, that kind of thing, we're good to go. All right, so you just add those up, the number of moles will add up, and we saw that when we did the Dalton's Law problem too. Okay, another problem that we're going to be doing with this is taking a look at a balloon when we've got oxygen and we've got chlorine. Okay, and we've got these, notice that it's going to be a certain pressure at torr. Okay, so remember what we do. We add up those number of moles. Let's convert my 2.1 grams of oxygen, and I also have 5.2 grams of chlorine gas. Okay, and so if I do that, that's going to be 32 grams of oxygen to 1 mole of oxygen, and that will give me 0.066 moles of oxygen gas. Now, I do that simultaneously with 71 grams of chlorine gas to 1 mole of chlorine gas. That will give me 0.073 moles of chlorine gas. So total in there, I have 1.39 moles total. Okay? So it's 1.39 moles total. They want to know the partial pressure of each gas in the balloon. Okay? Well, if I do that, if I take a look at that, and I want to see the mole fraction in there, okay, I want to know the total pressure, the partial pressure, and we know that the total pressure is 748 torr. Okay, so the total pressure, okay, where is it? Here it is. The total pressure is going to be 748. Well, this is a mole fraction problem. So it's basically saying I want to know the individual parts. So if I divide my 0.066 by the total number of moles of 0.139, I see a mole fraction of 0.47. If I divide my 0.073 by the 0.139, the mole fraction of my chlorine is going to be a 0.53. Remember, these guys are going to add up to 1. So what I can do is I can then say, whatever this is, the fraction of this system is going to be 0.47 oxygens. I can simply take my 748 torr times the mole fraction of oxygen of 0.47, and I would get my 351.6 torr of oxygen. And then I do the same thing, 748 torr by my 0.53, which is the partial pressure of carbon, or the the mole fraction of my chlorine. I get 396.4 torr of chlorine. Okay, so to do this problem, I would simply take a look at a mole fraction. Okay, pretty straightforward with those types of problems. It's probably the cleanest way to go about doing these. There's a couple other routes you could take, but that's probably the easiest. So we're going to be taking a look at what happens, first of all, when we take methane and convert it to carbon dioxide. We've seen a problem like this before, but now we're going to be looking at the mole fractions of each of the gases in turn, assuming that all your methane is going to be converted over. Okay, so I see my balanced equation up here, and what we need to do is we need to see the mole fractions of oxygen and carbon dioxide and water when I have 1 mole of this, okay, with 4 moles of oxygen. Okay, so I've got my components all labeled up in here. We solve for my carbon dioxide, we solve for my water, we do all those fun things. All right, so let's take a look and go 1 mole of CH4, and we're going to convert 1 mole of CH4 to 1 mole of carbon dioxide. That will give me 1 mole of carbon dioxide. That will also give me 2 moles of water, won't it? So if I converted my methane to water instead, that's a 2-to-1 ratio. Okay, so that's the pretty easy format for that. Now, if I had and used up all of this mole of methane, then I could say, well, okay, if I have 1 mole of carbon dioxide in there, 1 mole of carbon dioxide to 2 moles of oxygen, and I'll explain that in a moment, we're going to get 2 moles of oxygen used. That means that I have 2 moles of oxygen remaining. Now, the reason I went this route, guys, is because they said the following reaction, assuming the methane, all of the methane is used up, you could solve this as a limiting reagent problem, but they're already telling us all of this is going to be used, and so we know we have excess of this guy. So I didn't have to solve it that way or treat it that way, okay? So I could figure out the mole fractions of that, and I would just be using up these, and we would get 2 moles remaining from there. So this is how many are produced and the 2 moles remaining. That's why I had to do that next step, okay? So pretty straightforward. It was not a limiting reagent problem. It certainly could have been, but they told us what was going on in the first place. So if the total pressure of the mixture is 1.26, what do we do then? Well, remember, with my values, I had, of the things that are remaining, I had 2 moles remaining. And remember that I had 1 mole of this produced, and I had 2 moles of this produced. There was 0 at the end of all of this, okay? And so if I look at it this way, 2 moles plus 1 mole plus 2 moles, these are additive, that ends up with 5 moles of gas total. Okay, and so what I can do then is take a look at the partial pressure is the 1.26. Well, okay, so what does that mean? Well, 2, if I was going to be looking at my oxygen, 2/5, 2 divided by 5 will give me a mole fraction of 0.4, and that's going to be oxygen. If I look at my carbon dioxide, that's a 1/5. Okay, and that gives me a 0.2. Oops, that's a 0.2, and that's going to be of my carbon dioxide. Sorry about that. That's a 0.2. And then lastly, my water is another of the 2/5. That gives me 0.4. And that's going to be of my water. So remember what we do with these mole fractions. I take my 1.26 times my 0.4. That will end up giving me 0.504 atmospheres of my oxygen. That's also going to be 1.26 times 0.4. That gives me 0.504 of my atmospheres of my water. And then lastly, 1.26 times my 0.2, that will end up giving me 0.252 atmospheres, and that'll be of my carbon dioxide. Okay, so mole fractions will give us our pressures, and so pretty straightforward. I'm taking a look at the total pressure once the total pressure is given. Okay, switching gears a little bit, we can also analyze one piece of the gases with regards to their root mean square velocity. In other words, how fast are these gases going to be going? I always joke in general chem that the gases are going to follow the universal laws of gym class, which is that chunky runs slow. The larger gases, in fact, do move at a slower velocity than the smaller gases, okay? So to actually calculate this out, we use this equation. Okay, the root mean square is the velocity, root mean square velocity is a function of the square root of 3 times RT divided by the molar mass, but that's got to be in kilograms. Okay, my R value is going to be a little bit different in this case. Notice it's 8.3145 joules per mole. Okay, so just be careful of your units along the way. Now, that's going to give us the molar mass in kilograms, and that's going to be also the moles. Okay, so let's take a look and calculate the root mean square velocity of helium when we're in, and oxygen gas when we're in 25 degrees Celsius. All right, So how we do this is we take a look and we see that the helium is going to be the root mean square is going to be the square root of 3 times my 8.3145 times my 298. Okay, so that's just the constant for everything, and it's really about the mass. Okay, so helium, remember, is 4 grams per mole, so that's 0.004 kilograms. So if I calculate that out, it is going at a velocity of 1360. Now, what that is going to be a meters per second. Okay, now I'm going to compare that to my oxygen. Okay, so my velocity, the root mean square of that is going to be the square root of 3 times my 8.3145 times my 298, and the mass of oxygen is 32 grams per mole, so that's a 0.032 kilograms. Just got to remember to put that into kilograms, you're good to go. That will give me 481 meters per second. Okay, those are the root mean square. Now you know what I mean by chunky run slow. He's pretty hefty compared to the helium, and so it's moving at a much slower rate. Very, very simple types of problems. Just know how to plug it into the equation with it. Now, a couple other things with this. Effusion of gases is going to be going through a hole in a chamber, and diffusion of gases is just openly mixing gases. And it is directly related to effusion, but diffusion is just the movement rather than going through a hole in a chamber. Okay, so Graham's law of effusion and diffusion really are the same thing, where you take the square root of the opposite. Take a look at those and track them, and we want to know, for example, how much faster, how many times faster a gas will effuse or diffuse compared to something else. So you sometimes see effusion and sometimes see diffusion. The difference is if they're going to be passing through anything, something. Okay, so let's take a look at where helium is compared to nitrogen gas. Well, if I track this a little bit, I see helium and nitrogen. And I do know, or sorry, not nitrogen, it's nitrogen dioxide. Excuse me. And so that's going to be a function. If I got my helium on top, remember that my helium is on bottom over here. And so my nitrogen dioxide is 46 grams per mole. And so I see, if I calculate this, divide and take the square root, I see that my helium is 3.4 times faster. Okay, and that is my helium. Just make sure if you got helium here, helium's down here in the equation. Okay, I could do it with that one, and if I was going to take a look at another example, I would say, I can't even remember if I've got this in the PowerPoint. Nope, I don't. Let's do one more with that, and that's going to be comparing then. Just one more time. Let's do one more. Let's do with now ammonia, NH3, to hydrochloric acid. Okay, so just adding in one problem here. Well, ammonia is the NH3 compared to my hydrochloric, and so that's going to equal the square root of my ammonia, which is 17, and is down in the denominator, and my numerator is going to be 36.5. Okay, just add it all up, and I see that my ammonia is actually, in fact, 1.5 times faster. Okay, at a rate of 1.5 times faster. So my ammonia is this. Now what that means is if I see that this has gone 1 meter, okay, I know that this guy will end up being, because he's 1.5 times faster, he'll have traveled 1.5 meters. Okay, if my hydrochloric acid has gone 10.3 meters per second, well, that means that this is going to go 1.5 times faster. So if I multiply that by 1.5, my NH3 then will be going 15.2 meters per second. Okay, so you can see what we're doing and why I added this other problem. We can see how many times faster, but I can also see if something went a certain distance, how far the other one will have gone. Okay, so that's all we needed to do for this particular section. Take a look at some applications and take a look at how we can apply that to identify different gases or see the distances they go. Mole fractions, effusion rates, and real gases. That should be good enough for you guys, and you should be well on your way.